means that you need to find a z from this equation and substitute the z here. Huh? So in these situations, you needed to solve this equation first. And get the z will be a function of n, v, n0, and t, and substitute that in the second equation. Second equation is the equation of pressure. G5/3, exactly this z. So it's very complicated. If you do this, you can find the equation of the state. Actually, they show that it needs you know how to reverse the series, you know. So it needs that you know the technical reversing the series, inversion technique. So you have this series, for example. And I want you to give me the x. What will be the x? X will be v0, v11, huh? This, huh? I want you to find for me the b, reverse inversion. How you can do that? You can take this x and put it here. Y will be a0 plus a1, b0 plus b11. I don't know how many order you want. And you will see that here there is only one a y and the other y are 0 here, the coefficients. So you can find for me the a0 and b0 and b1. This is a very hard actually, but if you do that, you will find that PV over n cut t, generally speaking, will be like that. This V here is 1 over n. 1 over n V, or V and O, is V and O. So, and lambda is function. So this equation is called an equation of a state. This is not PV and cut t, this is a PV and cut t multiplied to some other function. This is the real equation of a state for the boson. And the coefficient which given here is I1 is 1. A2 is, this is a credit, you needed, I don't think that you needed to write a program for that, but you can use it the mathematical and define the days or maker. They can make inverse the series for you. You give the series and they give you the inverse. There is also equations for that. In the textbook you can find the equation which they give you B0 in terms of the other A. They give you B1 in terms of the other A. So this is the real equation of a state. So now I want to talk about the situations with the when the z tends to the near 1. So any system, any bosonic system has a regime of the ideal graph equation of a state. You see that PV and Kt also recovers when Z is very, very tiny number. So, and now I want to talk about this theoretical phenomenon which happened here. The theoretical phenomenon which happened is exactly as I told you that when will be important when n0 will be very, very big number, even bigger than the n. In this case, the z can be remain close to the 1. What is special about this? Special about this is came from this equation. Look at these equations make it a plot for that for me. If you make a plot of G over T, if you put it the Z here, and this is G over 3, it starts from 0 to 1. This is a monotonically increasing function. Monotonically positive increasing function. And always remain less than Riemann function at the 0 over 2. This is a given number. Kc 3 over 2 is a number, radical something, like a p or something. P over a square, p square over something. Anyway, these functions g3 over 2z is always remain less than that. What you understand is that this whole quantity will be less than that, less than this. So n over, what is the n minus n0? N minus n0 is n excited, huh? The one which is seated in the any energy with upper than the ground state. Total number, the number sitting E0, so this is given the rest number of the particle. So just you can see that this is a less than 1 over 2 VKC over 2. Yeah, because of this. And this is NAE. So you see that the NAE will be less than V. You know what I did? I just replaced the lambda. You know, lambda was h radical 2p mkt. I just replaced it and this. So it seems that the NAE always remain less than the numbers. Always. It cannot exceed, never exceeds from this upper bound. The maximum, what is the maximum NAE? The maximum NAE is when NAE is equal to that. This will be the maximum. Okay, I want to see how much is the maximum NAE, and after that, how many particles will be sitting in another state. So, we divided the system to two levels. One is the level with energy 0, with N0, and the other one, they are, we call it excited states. The total number of the particle here is NaX or NaE. Okay? And they cannot go far from this bond. What is the maximum NaE? The maximum NaE is when this will be equal. What is this number? I don't know. You needed to do the mass of the boson temperature.